Okay, let's take a look at friction. And by the way, I was just kidding about using Rebecca's answer key as the answer key because I make up my own answer key, but I do check hers first because usually I can find any mistakes on mine by checking against hers. But anyways, okay, so we want to look at friction. Basically, it's a force when two surfaces are touching, and we're going to talk about static friction and kinetic friction. Remember, force is a push or a pull, and we're going to be looking at these new things, including the idea of the coefficient of friction. So, friction always acts in the opposite direction to which you're pushing. If you push your hands across the table, friction tries to oppose your push. We really haven't been including friction in our forces up until now, but it is a universal force, so we're going to take a look at that. When you push a book across the desk, you experience a type of friction that acts opposite the motion. This force is known as kinetic friction. It's exerted between two forces that are trying to rub against each other. To understand the other kind of friction, you have to imagine something that is not moving yet, and you're trying to get it to move. When you're not putting any force in there, there's nothing holding it in place. As you apply more and more force, it seems like there's something holding it in place. That's static friction. This form of static friction is a force exerted on another surface when there is no motion between the surfaces. Again, the harder you push, the more the static friction is. If you're pushing a little bit, there's a little bit of static friction. If you're pushing hard but it's not moving yet, there's a lot of static friction. This is because static friction force acts in response to other forces. Finally, you can push it hard enough and the thing will begin to move. You've broken static friction no longer applies, and you're into the new type of friction called kinetic friction. Evidently, there's a limit to how much static friction force there can be. Again, once you get greater than that maximum force, you no longer have static friction, you have kinetic friction. So friction depends on the types of surfaces. If you have two rough surfaces, there can be a lot of friction. Ski, for instance, if you put skis on concrete, not going to go very fast. Skis on snow, not very much friction. Normal force between two objects also matters. In other words, if you have just a light object pushing down on the pushing the surfaces together, not a lot of force. The heavier the object is, pushing the two surfaces together, the more force. Again, we can measure this by pulling a block at constant velocity. Remember, as long as there's constant velocity, then the force that you're applying to pull the object is equal to the friction trying to slow it down the other direction. And so you use a spring scale and you pull a block across a surface. You can then add additional blocks. The more, and then you would increase the normal force. And repeat the measurement. You're going to find that the amount of the amount of kinetic friction goes up. In fact, you could see it plotted on a chart like this. So here we have kinetic friction. As the normal force goes up, as you have more and more weight, the kinetic friction is going up. It'll go on a linear relationship. You'll notice that the sandpaper has a steeper linear relationship than a highly polished table. In other words, it takes more force to overcome the friction. And so the different lines then correspond to dragging the block across the surface. Again, it's pointing out that the sandpaper is steeper than the polished table. So you'd expect it harder to pull a block out in sandpaper than a polished table, so the slope must be somehow related to the magnitude of the resulting force. The slope of that line, we're going to designate as a micro symbol, and the K, basically that's going to be called the coefficient of static friction. I'm sorry, it's a lowercase mu and a k. Anyways, it doesn't matter. We're going to call it coefficient of kinetic friction between the two surfaces, and it relates to the normal force. And so if you looked at the chart, you'll notice kinetic friction up the side, normal force across the bottom, rise over run. Rise is kinetic friction, run is normal force, gives you the coefficient of friction. Okay, kinetic friction then is equal to the product of the coefficient of the kinetic friction times the normal force. So basically, if you move the normal force over to the other side of the equation and isolate the kinetic friction, you could calculate kinetic friction by taking the force, the coefficient times the normal force. Maximum static friction is related to the normal force in a similar way to the kinetic friction. Static friction, again, is the stuff that's trying to keep it from moving. If there's a force that's trying to cause it to move, the static friction will increase in value before it is overcome and the motion starts. Again, very similar equation. The friction force, static, is going to be less than or equal to the coefficient of friction times the normal force. So the static friction is less than or equal to the product. In the equation for the maximum static friction, now we're going to use mu s is the coefficient of static friction between the two surfaces, and so we can calculate the maximum static friction by multiplying the normal force times the coefficient of static friction. The equations for kinetic and maximum static friction involve only the magnitudes of the forces. The forces themselves are the friction forces and the normal forces, and they're at right angle to each other. So here we have a table of some kinetic friction and static friction. You'll notice that the static friction is always greater than the kinetic friction. It's harder to get something moving than to keep it moving. Doesn't matter whether you have glass on glass, steel on steel. Okay, so anyways, the rougher the surface, the higher both of the frictions are. And again, the static friction is always higher than the kinetic friction. Okay, so let's say you want to push a 25 kilogram box across a wooden floor at a constant speed. The coefficient of friction is 0.2. How large a force do you have to exert on the box? Again, this is just saying it's at constant speed. The velocity doesn't matter. The velocity is not used in the equation. You just need to know that it's at a constant speed. So the 1 meter per second doesn't even get involved. You do have to convert the kilograms, which is mass, into a normal force, and then take that normal force and multiply it by 0.2, and that's going to tell you what the kinetic friction, the force of kinetic friction is. So again, here we have the problem. We're pushing the box at a constant rate of speed. The worker's pushing in this direction, friction's acting in the opposite direction. If we kind of draw it out, we have the velocity we have velocity to the right, but zero acceleration. So zero acceleration means that all of the push force is going into counteracting the friction force. The free body diagram will show us the force of gravity, basically 25 kilograms times the 9.8 meters per second squared will give us the force of gravity. Since it's not rising up off the table, then the normal force is equal to the force of gravity, so we know what the normal force is. Friction force is acting in one direction, the push force is acting in the other direction, and the net force is 0. No, net force of 0 doesn't mean that there's no motion, it simply means that there's no acceleration. It's moving, it's just not accelerating. So again, this is kind of a red herring in here, this giving of velocity. This is the important part, acceleration 0. So we're going to solve it by first of all figuring out what the normal force is. And then we're going to figure out how much the push force has to be by taking the normal force times that 0.2 coefficient of friction. And we get our force on the box. And so are the units correct? Yep. We want it in newtons. Do the signs make sense? Yep, they agree with the sketch. And is the magnitude reasonable? Yeah, it's pretty reasonable for a 25 kilogram box. So, we're done.